In the last lecture, we had solved the problem of the temperature conduction in a composite material, and we had calculated what is the correction to the thermal conductivity of the composite material due to the presence of particles of thermal conductivity Kp and volume fraction phi in a matrix of volume fraction of thermal conductivity Km. And in order to solve this, if you recall, we had solved the temperature equation in a spherically symmetric in a axisymmetric configuration, okay, where we had applied a temperature gradient at the z direction far from the particle, and the temperature field was only a function of the radial coordinate r and the azimuthal coordinate theta. Okay, so, we had basically solved the Laplace equation 1 by r square d by dr of r square partial t by partial r plus 1 by r square sin theta. Sin theta partial t by partial theta, this is equal to 0. Okay. Now, there could be problems where it is not axisymmetric. Okay. There could be problems where it is not axisymmetric. In the axisymmetric case, we had shown that the temperature field has to be of the form sigma over n is equal to 0 to infinity of a n r power n plus b n by r power n plus 1 into p n of cos theta. Okay. So, this depended only upon theta, where p n of cos theta is the Legendre polynomial. Is the Legendre polynomial. And it satisfies an orthogonality relation. Okay. Integral d theta, sorry, it should be sin theta d theta in a spherical coordinate system. P n of cos theta, P m of cos theta is equal to 2 delta n m by 2 n plus 1, where n has to be an integer. Okay. We got that the solution is finite at theta is equal to 0 or pi, or at cos theta is equal to minus 1 or plus 1 and plus 1, only if n is an integer. Okay. So, those were the solutions. What happens if we have a coordinate system that is not axisymmetric? Okay. What happens if we have a non-axisymmetric temperature field? Okay, what happens if we have a non-axisymmetric temperature field? Okay. In that case, the governing equation is 1 by r square d by dr of r square partial t by partial r plus 1 by r square sin theta is equal to 0. So, that is the temperature field. Okay. And rather than solving this for a specific problem, we will just look at some general properties of the solution of this temperature field. Okay. We will look at some general properties of the solution for this kind of a temperature field. Okay. So, we have to do the separation of variables step by step, starting with the phi direction and then the theta and then the r direction. I will go through that in a step by step manner. Okay. So, in this case, the temperature field has to be written as some function of r, some function g of theta, some function h of phi. Okay. and then I have to divide through substitute into the equation and divide throughout by f, g and h. Okay. So, if I substitute into the equation and divide throughout by the product f, g and h, I will get 1 over f r square d by dr of r square partial f or df by dr, okay, because I am using separation of variables. So, f is only a function of r, g is only a function of theta and h is only a function of phi. One over g r square sine theta this is equal to 0. So, this is the equation that I get. I can make the last term only a function of phi by multiplying throughout by sine square theta. Okay. So, I can make the last term only a function of phi by multiplying throughout by r square sine square theta. So, I multiply this equation by r square sine square theta, okay, and I will get sine square, rather I can write this as r square sine square theta into 1 by f r square d by dr of r square df by dr plus 1 by g r square sine theta plus, okay, this whole thing plus 1 over h d square h by d phi square. This is equal to 0. There are two terms on the left. The first term is only a function of r and theta. The second term is only a function of phi once I multiplied throughout by r square sine square theta. Okay. The first term is only a function of r and theta. The second term is only a function of phi. That means that both of these have to be constants. Okay. So, the function of phi, I require that 1 over h d square h by d phi square. This is equal to some constant, okay, alpha. Okay. How do we determine what is this constant alpha? Okay. In a spherical coordinate system, okay, in a spherical coordinate system, okay, this is r, this is theta, okay, and this angle around the axis is phi. Okay. This angle around the axis is phi. Okay. This is x, y and z, okay, and phi varies from 0 to 2 pi. Okay. Phi varies from 0 to 2 pi. Okay. As I go around the z axis in the phi direction, okay, if I increase phi by 2 pi, if I increase phi by 2 pi, I return to the same physical point in space. Okay. When I increase phi by 2 pi, I return to the same physical point in space. Okay. Therefore, because of this, because phi goes from 0 to 2 pi, and when you increment phi by 2 pi, you return to the same physical point in space, there is a condition on h, that is that h of phi plus 2 pi is equal to h of phi. Okay. In fact, you can go as many times as you want around the axis. Okay, you can go as many times as you want around the axis. So, phi plus h of phi plus 2n pi is equal to h of phi. Okay, you can go as many times where n is an integer. Okay. Let us look at the solutions of this equation. Okay. 1 by h d square h by d phi square is equal to alpha, which means that h is equal to, if alpha is positive, h is equal to a e power alpha phi plus b e power minus alpha phi. Okay. So, these are exponentially increasing and decreasing functions. Okay. These are exponentially increasing and decreasing functions, and if you increment phi by 2 pi, you do not return to the same value of the function. If a function is exponentially increasing or is exponentially decreasing, right, if you increase the argument phi by 2 pi, you do not get back to the same value, except for some specific values of b, a and b. However, even for those specific values, if you increase phi by 2 pi, then you go to some other value of h. Therefore, if alpha is positive, you cannot satisfy the condition that when you increase h by when you increase phi by a value of 2 pi, you come back to the same physical location in space. Okay. The only way you can satisfy it is if alpha is negative. Okay. If alpha is negative and alpha is equal to minus m square, minus m square, then h will be equal to a e power I m phi plus b e power minus I m phi. Okay. Alternatively, I can write this in terms of sine and cos functions as c cos of m phi plus d sine of m phi. Okay. When written in this manner, a and b are of course complex numbers. Okay. The constants are complex numbers. Okay. You can see that these sine and cos functions, cos of m into phi plus 2 pi is equal to cos of m phi plus 2 m pi. Okay. This will be equal to cos of m phi, that is h of phi plus 2 n pi is equal to h of phi only if m is an integer. Okay. This will be equal to, so when you go around by 2 pi, you will end up with the same value of h at phi plus 2 pi as at phi is equal to phi only if m is an integer and the increment in the angle is 2m times pi. Okay. So, therefore, physically realistic solutions which give you a unique temperature at a fixed point in space, even when you increment the angle by 2 pi, these solutions exist only if this 1 by h square d square h by d phi square is equal to m square and m is an integer. Okay. This you can write it either as in terms of e power I m phi or in terms of cos and sine m phi. Okay. Okay. It can be written in either of these ways. Okay. For the present, we will select this for writing our solutions. Okay. We will select this for writing our solutions. Okay. So, if I write h in this form, I can write h as a m e power I m phi, where this e power I m phi contains both a sine and a cos function. Okay. If I take the real part of this, I will get two constants. So, I can write this as the real part of a m plus I times the imaginary part of a m times cos phi plus I sin phi. Okay, so there are so this gives me a real solution which is real of A m cos phi minus imaginary of A m sin phi plus I into real part of A m sin phi plus imaginary part of A m cos phi. Okay. So, that is how I would expand out a general solution where the coefficient contains both real and imaginary parts. Okay. I said here that m is an integer, okay, and for integer m you can write the expansion in one of two ways. Okay. You can either write h is equal to summation m is equal to 0 to infinity of a m e power I m phi plus b m e power minus I m phi. Okay. That is one way to write the solution for positive integers. The other way to write the solution is basically just the summation m is equal to 0 to infinity of a m e power I m phi. If m goes from minus infinity to infinity, it includes all integers. Okay. So, I do not have to have this second term. Okay. We will choose this notation here. Okay. We will choose this notation where m as an integer goes from can have both negative and positive values. Okay. If you constrain m to have positive values, then you have to include both e power I m phi and e power minus I m phi. Okay. Right. So, when you write the function in terms of a complex function, if I write h is equal to a m e power I m phi, okay, the orthogonality relation. Okay, so I'll just take the function h as e power I m phi. Okay, the orthogonality relation has to be expressed in terms of the complex conjugate. Okay, integral 0 to pi 2 pi d phi h of phi with m. Okay. Okay. If I write the solution h m is equal to e power I m phi. Okay. H n star of phi, the complex conjugate. Okay. This is equal to integral 0 to 2 pi d phi, okay, of e power I m phi e power minus I n phi. Okay. Each of these can be written in terms of cos and sine functions. Each of these can be written in terms of cos and sine functions. Okay. Note that the complex conjugate, okay, h star of phi is equal to, okay, if h m of if h m of phi is equal to e power I m phi, okay, which is cos of m phi plus I sine of m phi, right. Cos and sine are real functions. Therefore, the complex conjugate h star of phi is equal to cos m phi minus I sine of m phi, okay, which is the same as, okay, h minus m of phi. Okay, because if you take h minus m of phi, you get cos of minus m phi plus I sine of minus m phi. Cos of minus m phi is cos of m phi, sine of minus m phi is minus sine of m phi. Okay. So, therefore, this can be alternatively written as, okay, h m of phi times h minus n of phi. Okay. There are two different ways of writing the identical result. The complex conjugate e power minus I n phi is h minus n of phi. Okay. So, this is equal to integral 0 to 2 pi d phi, okay, of e power I m phi e power minus I n phi. Okay. And you can see that each of these terms contains sine and cos functions. Sine and cos functions of m phi and sine and cos functions of n phi. Okay, they contain sine and cos functions of m phi and sine and cos functions of n phi. And each of these integrated from 0 to 2 pi has to be equal to 0. Okay, when you go around and come back to the same point, integral of a sine function between two limits 0 to 2 pi has to be 0. Integral of cos function has to be 0, because integral of sine is cos, that cos is the same at 0 and 2 pi, okay, and so on. So, this will be 0 unless m is equal to n, okay, unless m is equal to n, in which case the integrand becomes just equal to 1. Okay. Okay. So, therefore, this is non-zero only when m is equal to n. Okay. Okay. This is non-zero only when m is equal to n, and when m is equal to n, this is delta m n, okay, times 2 pi. Okay. When m is equal to n, this is equal to 2 pi, because integral of 1 times d phi between 0 and 2 pi is just 2 pi, otherwise it is 0. Okay. So, that is the orthogonality relation expressed in terms of the complex exponentials. Okay. That is the orthogonality relation expressed in terms of complex exponentials. We had derived the orthogonality relations earlier when it was expressed in terms of sine and cos functions. Okay. So, in this case we express it in terms of complex exponentials. Okay. So, that is the h direction, okay, that is the phi direction. We have the other two directions here. Okay. We have the other two directions here. Okay. So, this thing was equal to minus m square. That means that this whole thing here has to be equal to m square. Okay. If the second term on the right is minus m square, first term on the right, second term on the left is minus m square, first term on the left has to be m square, so that the sum of these two is equal to 0. R square sine square theta. This is equal to, okay, this thing has got to be equal to m square. Okay. Okay. Now, we can cancel out the r square here. This should be, I am sorry, this should be r square sine theta. So, this r square will cancel out, and I divide throughout by sine square theta. Okay, divide throughout by sine square theta. Okay, and I will get 1 by f d by dr of r square df by dr, okay, plus, okay, 1 by sine theta d by d theta of sine theta df by d theta, sorry, dg by d theta. This should be g, please correct that. Okay, the first term is proportional to f, the second term is proportional to g. Okay. Okay. Minus m square by sine square theta is equal to 0. Okay, so, this is the equation after I have divided throughout by sine square theta. Okay, after I have divided throughout by sine square theta. Okay. And here you can see this first term is only a function of r, The second and third terms are only a function of theta. That means that both of them have to be constants. Okay. Okay. The first term is only a function of r. The second term is only a function of theta. The second and third terms on the left are only a function of theta. So, both of them have to be constants. So, if I take these two terms, okay, if I take these two terms here, okay, multiply throughout by g, I will get 1 by sin theta d by d theta of sin theta dg by d theta minus m square g by sin square theta is equal to 0. Okay. If I substitute psi is equal to cos theta and d psi is equal to minus sin theta d theta. Okay. Then I will get d by d psi just as we had got earlier of sin square theta here dg by d psi minus m square g by sin square theta. This is equal to 0. And this sin square theta is equal to 1 minus cos square theta. So, I can just write this as 1 minus psi square and if m were equal to 0, this was the same Legendre polynomial that we had got. Okay. I am sorry, this should be a constant. Okay. This should be some constant c. Okay. The first and second terms have to individually be equal to constants. This will be a constant c. Okay. Recall that for m is equal to 0, okay, for m is equal to, sorry, so let me back up a little bit. So, this is we had a 1 over g here. Okay. Okay. We substitute this and multiply throughout by g. Okay. Substitute this and multiply throughout by g, and I will get a constant times g over here. When m was equal to 0, okay, we had got the same equation for m is equal to 0 when we did the temperature field around a spherical inclusion. In that case, m was equal to 0 because there was no dependence on phi. In that case, we had got the solutions as Legendre polynomials. Okay. In this case, what are the solutions that we get? Okay. So, I will explain that the solutions that we get in this particular case, I will start explaining that in the next lecture. Okay. So, I will continue the separation of variables in the theta direction and then go on to the separation of variables solution in the r direction. Both of these I will continue in the next lecture. I will see you then.